Let's talk about area between two curves, but this time the curves are going to be given as functions of y. So imagine x equals e to the y is the red curve, x equals y squared minus 5 is this fella here, and we're being asked to get the area between the curves starting at -1 and finishing at 1. And what we said is that to do that, you find the integral from y equals -1 to 1. It's essentially f of y take away g of y. And I hope I mentioned it at the end of yesterday. Is the red one going to go first or the blue one going to go first? Because now we're orientating in a left-right direction. Can you remember whether it's the red curve that goes here or the blue curve that goes here?
Red curve is f of y.
Correct. And the one that's furthest to the right is the f of y, right? So that's basically f of y, and this is the g of y. So isn't it very similar to what you would have done if it had been a curve that looked that way, right? You would have done top, take away bottom from here to here, right? So the formula doesn't change much even when you change the orientation to be in terms of y. I would probably, in this question, do that. If each of the terms is easy to integrate, then you pretty much just do it in one go. So antiderivative is this guy, power rule, add 1 to the power, divide by the new power, and the 5 gives me 5y, and we'll be doing it from y equals -1 to y equals 1. Now, if you plug in 1 here, you'll get e to the 1, take away a third, plus 5. And if you plug in -1 here, here, and here, you get e to the -1. I'm skipping a line here. If you plug in -1 in here, -1 cubed is -1, times another negative is why that's plus a third. And if you plug in -1 here, it's -5. Are you comfortable with me doing that in my head? You can write it down in full if you're not 100% sure where each of these come from. Plug -1 in here, here, and here, and these are the terms you get. In this case, that's e. I'm just going to leave them alone. That guy, I'm going to call it 1 over e because it looks better that way. And 2 negatives make 5. So I'm going to have an e. I'm going to have a takeaway, a 1 over e. And that guy, that guy, that guy, and that guy, or whatever my calculator says it is, what's that, 10 take away 2/3, that's 9 1/3, so that's 28/3. So if you take care of these 4 guys on your calculator, you'll get 28/3, and this rather ugly looking thing is the area between those 2 curves. So if you think about what we did yesterday, isn't it very, very similar, right? You need a start and finish value, right? So essentially use Desmos to draw it if you need to. That step doesn't always need to happen. Find the limits of integration, -1 to 1, and the order of subtraction, this guy, take away that guy. And then integrate, which is pretty much what all of this was to get your answer. In this particular situation, it was just what? We know that because it's a standard integral and 2 power rules. Any questions about that, or can I move on? We're good? Okay. All right. Next question is like 14. And we have x equals 7y squared. And we have an x equals 8 plus 5y squared. And we're being asked to find the area enclosed. So the key word here is enclosed. So I'm going to drift over here and we'll do step 1, which is Desmos. Now it's going to be x equals 7y squared, so I'm just going to do it this way. Hit enter. And then I'm going to do x equals 8 plus 5y squared, which is that. If I shrink it back by just using my mouse scroller, it is not at all clear because at this end especially, things compact together a lot. So I'm going to go here and I'm going to notice that really anything around about 4 and -4 is all I need for the x's. So I'm going to change that first. So I'm going to do x is -4 and I'm going to change this cell up to +4. And I did the wrong one there, but I'll come back to that. It's the y's that are -4 to +4. Okay, now if I click out that and I shift this a little bit, can you see that the two curves are a little bit easier to see, but I've certainly not got a very good x value. So I'm scrolling along here to, I think, the join's about 28. So I'm going to go here and I'm going to make this guy 0 and I'm going to make this guy 28, and let's see what we get now. Hey, oh, that guy switched on me, the little darlings. There we go. Now, I would like to know where the intersection of these two curves are. And if I click on this one, you can see the coordinates of it. And if I shift it along a little bit and I click on this one, you can see the coordinates of it. So it looks like they intersect at 28,2. So I'm going to draw, let's shrink that back a little bit so I can see some stuff. Right. So I'm going to draw one curve going like this, and the next curve going like that. And the one that's green is x equals 7y squared. And the other one is going to be called 8 plus 5y squared. So Desmos wasn't great. Sometimes the functions are just awkward. But that's the gist of what we want. So you might say, well, what's the area they're talking about? They're talking about this area here. Right. Enclosed is one curve cuts in the other, and they want the piece where they overlap. That's what enclosed means. So in this case, you can see this curve and that curve. They make this funny little shape. I need to know the coordinates of these because I'm going to be doing these questions in terms of y. So I need to know where this guy is and where this guy is. And very often in Desmos, it's easy to tell what that is. But in this case, there's another way I can find out. If I want to know where this curve intersects with that one, can't I just make them set them to each other? Right, make them equal to each other. Now, if you take away 5y squareds from both sides, and then you divide, you get plus or minus 2. So that guy's 2, and that guy's -2. So I did find them. I don't think Desmos really helped me because they were, you know, when we did Desmos, the two things looked like that, and it was really hard to tell where the intersection was, so I had a backup plan. So it's pretty much ready to go. I got my picture. To find the area between them, I know y is going to go from -2 to 2. One of these curves goes first, and one of these curves goes second. And this one and that one. In this case, that one, right, same. He's to the right. Take away this one. And then simplify. And then all I need to do, power rule. Evaluated from -2 to 2. So y is -2 to +2. The curve that's furthest to the right was this one. Take away the other curve, which is that one. Combine them together by basically combining like terms. Power rule to integrate. Plug in 2. Well, if you plug in 2 here, you get 16. If you plug in 2 here, 2, 4, 8, you get 16/3. Take away, if you plug in -2 here, you get -16, and you get plus 16/3. And if I go to my calculator, I should be able to do that. It's basically 16, take away 16/3, add 16, take away 16/3, and then hit the math button, choice 1, which says turn it into a fraction, and the answer I get is 64/3. So if you want to find the area between two curves, but the curves are given as functions of y, this is essentially the process. Take Desmos, it'll give you an idea of who's to the right and who's to the left, because that tells you who goes here and here. And if you're really lucky, Desmos will tell you the intersection points, which are these two. If that's too hard to do, you have a backup plan. Set the equations, set these equal to each other and solve the equation. Once you've got the integral set up, it's really just, plug and chug, power rule. Is there anything about that question? Are we good? Very good.
Just a quick question. So, sure. Just to understand, these are all very symmetrical along the y-axis. So it's plus or minus -2.
Yeah.
But we also set the equations equal to each other to find limits that aren't always symmetrical, like plus or minus, the same number with y.
Yeah. If I changed one of these equations a little bit and I set them equal to each other, that top might be 3 and this bottom one might be -1. So there's no particular reason why they need to be symmetrical. They just happen to be in these questions. And if you do it in Desmos and it's nice, you should be able to find these guys by just clicking on them and it'll tell you the coordinates. This one will probably be something like 28,2. I think that's actually what it was, 28, -2. If you did it in Desmos. And this guy up here would be, let's try that again, 28, -2, and 28, +2 would be that one. So if you clicked on it, Desmos would tell you the coordinates, but it was a bit hit and miss. This here is just a backup plan that you only really need to do if it's not obvious. See, if I was doing a different curve, right? Imagine one of the curves looked like this, and the other curve looked like that. I think Desmos would be able to find these 2 points very easily, right? You could just click on them. Let's pretend that point was 2,10, and this was 4, -5. Well, that would give me a y value of -5, and this would give me a 10. So you can see the y values are different. And then whatever this curve is, that would be my f of y, and whatever the equation of that one was, that would be my g of y. And that would allow me to set this up. If you can set this up, I think what happens after that is pretty standard, right? There's not a lot weird stuff that happens after you set it up.
Yeah, thank you. It makes a lot more sense.
Okay, thank you. See what we got cooking here. Here. Right, let's zoom over and see what it looks like in WebAssign homework. Make that a little bit bigger. Right, that's basically my version of 14. Do you see that there are 4 pictures here? And one of those pictures was actually what WebAssign would have done if I'd chosen better scales. It would have been that one. So that's the one you would have clicked. And then the integral, exactly what I did. Can't remember what my answer is. Whatever the real answer is, I'm pretending it's 42, right? You type it in there. Right, now, let's look at this picture. I should be able to make this a bit bigger. I want the area between these guys here. So I don't need Desmos. Isn't that picture essentially doing what Desmos would do for me, right? Now, looking at that picture, the area between the 2 curves is obviously this piece here, right? The Y value you get from here. And the Y value, I guess I'm just getting it because I can see that. Would you agree that's 0, 0, the origin? So the Y value would go from 0, and which of these 2 numbers would I finish with? Is it 0 to this number or 0 to that number? Which one should I use as my other Y value?
3 halves.
Agreed. So although you can't see this, I'm writing that down, 0 to 3 halves. Now, on that picture, one of them's f of y, the guy I write down first. Take away the other. So red or blue, who do I write down first?
Red.
Red.
Right, because it's furthest to the right. Okay, the one that's furthest to the right goes first. And in this case, it's the red one, so what's that? Y take away y squared. Subtract. Okay. Well, the other one is the blue one, which is y squared take away 2y dy. And now I'm going to go in to the whiteboard thing, and you can see that information all put together. The 0 to 3 halves, red guy, take away blue guy. That's the integral that you'll evaluate to get the area between those 2 curves. What should I do next about these 2 expressions? What should I do about them?
Should we just combine them first?
Yeah, I would. So that take away that means add, so you get 3y. That take away that, you get that way. Would we be okay for me to go dot, 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 dot now? Would you be able to do power rule on this integral? Plug in 3 halves, plug in 0, grab your calculator for the, the awkward numbers that you're going to deal with. And the answer's 1759, so whatever it comes out to be. Does that have a flow to it now? Are you beginning to see the more of these you see, hopefully the clearer the process becomes in your mind? You got a picture, you need to use the picture or Desmos to create the picture to get the start and finish y values. You need to know which one of the 2 functions goes first, take away the other one, go second, make it look pretty, integrate, answer. Let's look at the next one. Okay, this is 16. X equals 45 take away 5y squared. Just writing that down. X equals 45, take away 5y squared. And the other one is x equals 5y squared, take away 45. And we want to find the area enclosed by them again, right? So, I'm not sure if this is going to work. I hope it does. Are you looking at Desmos now? Will I have to go out with it? Oh, great. Saves me having to do a lot of work. Right. The first guy is x equals 45, take away 5y squared. Oh. And the second guy is x equals 5y squared. Yeah, it looks like they're going to do another one of those symmetric ones. There's no reason in the world they need to be symmetric, but they are, so they are. I'm going to shrink this fella back quite a bit, maybe shift it over a little bit and go in. Yeah. The area that's being enclosed is this area here in the middle that looks like, I don't know, a squash rugby ball or something, right? Can you see it? It looks like a big egg. Not a squashed egg. Right. Now, if I click on that point there, can you see its coordinates are 0, 3? So that tells me the y value is 3, and I bet you that one's -3, which it is. Black or red? Who goes first? Black or red?
Black.
And that happens to be 45 take away 5y squared. Subtract the red one, which is 5y squared, take away 45. Okay, now let me show you what I got from that picture. From -3 to 3, black guy, take away red guy. If it's possible, combine terms. 90, take away 10y squared, dy. Can I do my dot, dot, dot again? Isn't that just a power rule? Evaluated at y equals -3 and 3. And that's you finished. So area between two curves when the information is given in, f of x equals x cubed and f of x equals 2x plus 1. Today we've looked at area between two curves when the functions are given as functions of y. So what is left? Okay. There's one more situation we haven't dealt with. And it's the area between two curves that cross over. So I want you to imagine this is a very generic version of the problem that I have starting, say, at A and finishing at B. I have my function f of x, and it looks like that. And then I have my second function, and it starts here, and and it goes like that. And they cross over or intersect, and they intersect at an x coordinate of c. And I am interested, we are interested in that area. I'll tell you what the answer is not. Oh, I know how to do this. It's the integral from a to b of f of x, take away g of x, dx. And the reason that doesn't work, isn't there a crossover at this point where at the early part on the left-hand side, the blue guy's on top, right? And then the green guy's underneath. But from this point, doesn't it switch places? And now the green guy is on top and the blue guy is underneath. So we have to adapt this formula to account for the fact that there's now a crossover. Any idea how you think you might be able to cope with that?
Two different equations.
Sounds like a plan. So I'll do the first one from A to C. Blue guy, which I'm calling f of x, take away g of x. Add. So what's the second piece going to be? How would we get its area?
From C to B.
And who's going first now?
Green.
Which I'm calling g of x. You're right, the green one. So do you see that what you need to do if the question has a crossover is that you don't have a single integration to do. You've got to find where the two intersect, right, where they cross over, and find this guy and that guy separately and then add them up. So that's the adaptation, right? So there are not many like that. So I'm going to see if I can, I think there's definitely one, but there might be two questions where there is a crossover. So I'm trying to hopefully find, here's one. Oh, two. Okay, I think there's two. Maybe a third one I just can't find. Okay, here we go. This question has a y equals 7 cosine of 5x. That's one of the curves. And the other curve is going to be 7 take away 7 times the cosine of 5x. And we're only interested in the curve between 0 and pi upon 5. And we're being asked to find the area between these two shapes. Now, I don't know how this is going to turn out exactly. So I'm going to go to Desmos, and with a bit of luck, I'll get to see what's going to happen. So I'm going to be a little bit careful here about how I set up Desmos. It told me in the question that x is going to go from 0 to pi upon 5. So I'm going to go over my little graph setting, and I'm going to make x 0. And I'm going to make the other guy pi upon 5. Well, if I click on this guy, I can get the pi button and then just do divide by 5. And now I can close all those windows off. Now I'm going to put in the first curve, which is 7 cosine of 5x. And hit enter. And then the other curve is going to be 7 take away 7 cosine of 5x, which is fine. So let me close that off. I think I might, oh dear, we can't really do it perfectly, but that's fine. That's an annoyance. If I scroll out, you'll actually lose some of the information. So from what I can see, I think I only need to get to about 12. So I'm going to have to go back here and make that 0 pi upon 5. And I'm going to make the y value 0 to 10, not 0 to 12, I think you decided. Oh, it'll be lower than that. It'll be, see, -7 to 12. I'm just playing about with the windows, so I think I've got a decent picture. Okay, almost done. There. Okay, here we go. Shift it over a little bit. Can you see that crossover point right there? Do you notice it's very faint, but can you see it as pi upon 15? You see it, volume? So I'm doing a little baby sketch of what that looks like so I can, you know, play about with it. I got a guy that goes like that, which is the green one I'm doing right now, which is 7 take away 7 cosine of 5x. And then we got another guy, make him red. And the red one kind of looks like this. And he's just 7 cosine x, 5x. And that point there is pi upon 15. The guy at the end is pi upon 5, and that guy is 0. Right, everything I need now that I got from Desmos, I've kind of condensed into a little baby picture. That's what it looks like. And we are being asked to find this bit and this bit. So the area is going to be the integral from 0 to pi over 15. The red guy, take away the green guy. The red guy is this fella. Take away the green guy, or in my case, the blue guy. Right, that's this one. And then I'll add this one. And it's the integral from pi over 15 to pi over 5. And it's going to be switch places. This guy first, take away that guy second. So that's my first one, that's my second. I find this area separately, I find this area separately, and then I add them up. That is a lot of work. So I'll just do one of them. Let's do this one. The integral from here to here. This guy, take away that guy, ends up being what? Ends up being 14 cosine of 5x, take away 7. That's 7, take away a negative, adds it, minus 7. Okay. How am I going to find the integral of cosine 5x?
U.
A U sub. What U sub should I use?
X.
Agreed. I'm also going to separate these into two distinct ones. If you have to do something like a U sub, it's probably better just to have it on its own. So I'm doing this on its own and then taking away this. So the U sub is going to be 5x. You differentiate with respect to x, you're going to get a 5. The crossover is that, and divide everybody by 5. You get that. So this fella now becomes 14 cosine of u times 1/5 du. And this guy, well, he's basically 7x evaluated at these 2 points. This fella becomes 14/5 the cosine of u. This guy here eventually becomes 7 pi over 15. Integrate a cosine, you get a sine, so you get 14/5 sine u minus that guy. Switch it back to 5x, and now you can evaluate it at 0 and at pi over 15. Plug this guy in, and you get the sine of 5/15, which is a third pi. Plug in 0, you get 0, so you get take away 0. Okay, we're almost done. What's the exact value of the sine of pi upon 3? You got to have it somewhere, unit circle or whatever.
Square root of 3 over 2.
You got it. So it's 14/5 square root of 3 upon 2, take away 7/15 pi, and the 2's cancel, so you get 7/5 square root of 3, take away 7/15 pi, and you do not want to do too many of those questions because they take forever. And I've only done what he's equal to. Don't you have to do that guy next and what he's equal to? And then you add them all up, and that's your answer. So we still, if I had time, I would do this one, but that would involve me doing a whole load of work very similar to this one. And that's essentially how you do crossover questions, right? Where the thing crosses over so that for part of the time, one of them's on top, and then for the rest of the time, the other one's on top. So I'm going to now change topic. I am going to show you a shortcut. Do we like shortcuts? Now, the shortcut I'm going to tell you about can actually be used in some of the questions that we've done, but it can be used in the bigger picture. It can be used any time that this happens. I'm going to show you the antiderivative of linear function shortcut rule. So here is the function, and here is what its antiderivative is going to look like. And I want you to see if you can come up with what the shortcut is. If you have to integrate e to the 5x, you can do it with a u sub. If you do it with a u sub, the answer ends up being that. If you do e to the 3x, the answer ends up being that. And if you do it e to any linear function, the answer ends up being that. Can you see a pattern in the answers based on the original? Because that's essentially what the shortcut is. Can you see the pattern? You can use the pattern to get antiderivatives quickly without having to go through the whole u sub process. But this trick only works for linear. That means 3x plus 7, a half x minus 2, right? Don't try and use this rule if it's e to the x squared or something like e to the sine. No, don't do that. It doesn't work. But e to the 2x plus 1, e to anything linear, it does. Does anybody want to try and describe what you do in English? Because it's quite hard to describe in English, but if I'll take a shot.
Well, it looks like you take the exponent and take its derivative and then just divide the function by that derivative and keep everything else the same.
For e to the x, you do.
Yeah.
So for instance, if I wanted to do e to the 5x take away 2, the antiderivative of e is typically just e, right? And what's that guy going to get me? Well, its derivative gets me 5. You just stick a 5 there. So notice it's 1/5. Well, that's the linear shortcut for ease. Sine of 4x, cosine of 2x minus 1, secant squared 5x, and shorty guys to do it to, sine of 10x minus 1. Right. Antiderivative of the sine of 4x is negative the cosine of 4x and a quarter. Cosine of 2x minus 1, its antiderivative is positive the sine of that with a half. Okay, what do you think a secant squared 5x is going to get us? What's the antiderivative of just secant squared, normal secant squared?
Tangent.
Right, so tangent of 5x. What's the 5 going to do? How's it going to affect what's missing at the front?
You're going to do 1/5.
Can you see this shortcut? Can you imagine that that could speed up a whole load of integrals that you might have had to have done through U-subs? Everything I'm doing here is a U-sub question. You can get the answer by doing U-subs. So if you're not good at remembering shortcuts, that's how I would do it. Right, this fella here then, won't he be negative 1/10 the cosine of 10x minus 1? Antiderivative of a sine is a negative cosine. The 10x is where that 10th comes from. Do you notice that whatever that is, it still stays put? Isn't the only added bit a little fractional thing that you tag on at the front? And before you get too comfortable, what's the antiderivative of the cosine of a half x minus 2?
Would that be 2 sine of 1/2 x minus 2 plus c?
Oh, you've just gone and broke your rule. Nope. Isn't it 1/2? And isn't 1/2 2? It still works. Oh, let's chuck in some guys. What's the antiderivative of e to the 1/3 x minus 1? Antiderivative of this guy.
3e to the 1/3 x minus 1.
Right. This one's just to remind you. What's the antiderivative of 1/x?
Natural log of x.
Agreed? Natural log of x. So if I want to define the antiderivative of that, I have to think of it as a linear version of this guy, which means it's the natural log of 2x plus 7. And what's that 2x plus 7 going to get me? Well, its derivative is 2. It's going to get me a half. Do you know that means now that we can find antiderivatives of any linear function? By that I mean any function chain rule linear, right? So we don't need to do sine of a 2x plus 1 anymore. Can't we just do this shortcut and get its antiderivative without going through all the U-sub stuff? Okay, so for the next few minutes, I'm going to give you something to try out. So, and I've chucked in some that are not as obvious as others, and some that are. Okay, there's 4 questions. You got a minute. If you know what you're doing, they should take you 15 seconds. Because it's a shortcut, right? Shortcuts should be quick. Last few seconds. Well, I know some of you have got it, so I'm not going to let some of you answer so others can have a chance. So, Brendan, you have to sit this one out, right? But you can nod your head, right, when they give the right answer, right? So you could be the backup. Anybody want to give me the antiderivative of this one? Just share it out.
1/4 e to the 4x minus 1 plus e.
Okay, I see a nod there, Brendan. Okay. Anybody want to try the cosine one? And I did something a little bit sneaky here.
Is it the negative half sign?
Yes.
And then, of course, 3 minus 2x. I figured because it was a negative 2x, we'd have to have a negative instead.
Yeah. No, I never did that one, but you see the linear shortcut method works for those as well. So as long as it's linear, right? 4x minus 2, 2 minus 4x, don't matter. Doesn't matter if it's a half either, does it? So this is the next volunteer.
Would that be -2 cosine of 1/2 x minus 1 plus e?
I should see a nod right now, and I do. What about the last one? Anybody?
Half of the natural log of 2x plus 3 plus c.
Do you think this shortcut method is something that you would want to remember? If it's useful,